Hey everyone, welcome back to another session with OneClass. My name is Bassam, I'm an engineering graduate, and today we're going to be going through some physics problems at the high school and preliminary university level. So let's get started over here. Okay, let me just show you my screen. Okay, so this is question number 1 that we're going to be going through. So the process that we usually do is we go through what the Janine The Tutor answered this question, and then we're going to verify that the solution is correct on the side here with some step-by-step processes and anything we need to figure out this problem. So for the first question, we're asked, explain about gravitational potential energy. So essentially just the concept that we're looking at is gravitational potential energy. So reading on to the Janine Tutor's answer, the general form of gravitational potential energy is given as this. So there's just the general form when you have two masses attracting one another, and then we have r for the distance between the objects and g for the gravitational constant. So there's just some constant. And then here r is very, very large. Okay, when the distance between objects r becomes less, that means the object is near the Earth gravity at this time. Earth gravity dominates. So when r is very large, that's when we use this equation up here. But when it gets smaller, then the object is near the Earth, then we use this situation. So at this situation, the below formula can be used. So we use the energy is equal to mass times gravity times height. Okay, so here we have mass of the object, g is a constant, so 9.8 meters per second squared, that's just acceleration due to gravity, and then the height of the object off the mass of the Earth. So just to kind of summarize, there's two equations. The first equation, U, so U here stands for gravitational potential energy, is equal to negative the gravitational constant times the mass 1, capital M, and then mass 2, lowercase m. And then we divide this by r, which is the distance between the objects. So r over here. And then I believe the negative sign here is because it would be pointing towards the object that's pulling. So if we had m, a very large distance, r, and then a smaller m, so this is energy. So yeah, the negative energy has to do with whether which object is doing the work on the other object. That's essentially why this is. But essentially, for a very large distance r, you would just have to use this equation. And then the other equation that we talked about is U equal mgh. And usually for more complex problems, you'll probably use this formula a lot more. This formula up here, you end up just plugging in whatever values you're given. So you probably have mass 1, 2, you have the constant in r. So really, it's more plugging in. This formula is when you have lots of different energies interacting. This one you use a lot more for representing potential energy. So I believe there's a example down here. We'll run through this. So calculate the gravitational potential energy of a body of mass 10 kilograms. So we have m equals 10 kilograms and is 20 meters above the ground. So these are in the correct SI units, kilograms and mass, so we don't have to do anything there. H is 20 meters, so I'll put the units. And then we know g is 9.8 meters per second squared. That's just acceleration due to gravity. So here we just plug in these values, 10, 9.8, and h is 20. And this will give us, let me just plug into my calculator. Okay, so we have 10 times 9.8 times 20. And then we have 1960. So that's 1960 joules. So looking at the calculated answer by the junior tutor, so yes, this is correct. Another way to think about this, we know 9.8 is pretty close to 10, so just kind of a mental double check. If we do 20 times 10 times 10, we know that's about 2,000. This number is a little less, so that kind of makes sense. So this is the correct answer for this example. So we'll mark this answer as correct. So correct answer. Great job. And then we'll move on to the next question. So this is question number 2. Alright, so for question number 2, so this is a pretty broad question, a physics definition. So let's look at what the junior tutor wrote for this question. And the study of relation between matter and energy is known as physics. So main idea is the study of matter and energy. So whenever there's a situation where you have energy, forces, things being moved around, stuff like that. And then here are the branches. So I'm just gonna run through what these are, and then I think that should be good enough for the answer for this question. So we have the first chapter. So this will also depend on, you know, which physics textbook you use and kind of how it's sorted. But these are just general topics. So classic mechanics, thermodynamics and statistical mechanics, electromagnetism and photonics, relative mechanics, quantum mechanics, atomic physics, molecular physics, optics, condensed matter physics, high energy particle physics, and nuclear physics. So usually whenever I think about physics in general, what comes to mind is Newton's 3 laws of motion, kind of kinetic energy, potential energy, optics also as well, and then what else? These are just kind of some general branches, but yeah, that's kind of physics is essentially just studying matter, energy, how objects move, why certain objects react certain ways. Even kind of spring forces is in physics, pendulum movement, stuff like that. So this is kind of a very broad question. I'm not gonna go any further into detail. I think that's a good general overview of what physics is. So good summary. Good job. And we'll mark this as correct. Okay, let's move on to question number 3. Okay, so in this question we're asked kind of a very large, we can see there's like a very large paragraph, so we'll just read it all. The mean radius of the Earth is 3,959 miles. However, Earth is not quite a sphere. So right away we know we're given this number, so we should just keep that in the back of our heads. We want to use that to do a calculation later. The planet's west to east rotation, so it's telling us it's not a sphere. So the west to east rotation causes it to bulge at the equator. So if we think of the Earth, so I'll mark this as question number 3. So the Earth, I'm gonna try to. Okay, so this, it's not a perfect circle. Let's say this was the equator. So the radius this way, or the diameter, I believe. So the planet's west to east rotation causes it to bulge out at the equator. Earth's equatorial diameter is 12,756 kilometers, but from pole to pole, the diameter is 12,714. So we're saying it's 12,756 kilometers in the west to east, so in the equator diameter. And then the diameter pole to pole is 12,714. If flying east to west, just above the Earth's surface at 150 miles per hour, calculate time to circle the equator. So we're given also this diameter, because it's not quite a sphere, and that's 12,714. So 12,714 kilometers. Okay. So really they want us to focus on west to east, east to west. So they want us to focus on this number over here. So I'll highlight that number so we can remember to use that. So we're using most likely going to be using this question number. And they also give us 150 miles per hour as speed, so I'll write that down to the side. 150 miles per hour. So right away we can see that this is in different units. So we have kilometers and miles per hour, and then here the mean radius. So it gives us this radius as well. It's not really. I don't think this is really relevant to the question. It's more we're talking about using the diameter around the center, so the equator. So this number. So here, one thing to notice about this physics problem is they give you a bunch of numbers, but you have to kind of figure out which numbers you need and which ones you don't. So right away we can cancel out. We don't really need this number. Usually a good way to start off is just write out all your givens and then put a star beside the numbers that you will use, or just put like an X beside the ones that you don't use. And this will help you keep track of information. So we know this number is not really useful as well. We only really care about this, no, not this number actually, this number. Yeah, this is the number. We don't care about this number, pole to pole, we care about this number. That's what we're going to use in our calculations. So let's go through the junior tutor's answer before we complete the calculation. So the diameter of the Earth at the equatorial line is given as this. So this one. Or this. So they do the conversion. They don't really show the diameter of the Earth from pole to pole, and they do the conversion. So one thing to note quickly, so when you're converting kilometers to miles, so we know that the conversion rate is 1 kilometer. Well, this is all messy. So 1 kilometer is equal to 0.62 miles. So this is the conversion rate. So looking at this, we know we have to convert it into miles. We would multiply by 0.62 miles per kilometer. So we want the rate that puts the miles in the numerator and the kilometers in the denominator. And we know this will cancel out with this because kilometers is in the denominator, and we can see that these two cancel out. This and this cancels out, and we are left with miles. So really all we have to do is take this number, multiply by 0.62. Let's plug that into our calculator. 12,756, 9.62, and we end up with 79.08. So here they have 79.26, so it's pretty close. Let's just double check that we didn't do anything wrong. 12,756. Yeah, so it's close enough. It's in the ballpark, so it's maybe like 20 units off. That's all right though. So now the circumference of the Earth at the equator is given as this. So this is the equation for circumference, 2 pi r, or pi times diameter, because 2 times the radius is just the diameter. So circumference is, I usually use C, but we can use S for circumference. So S is equal to pi diameter, which equals, in our situation, so pi times 7926. So this will give us the distance our plane is traveling. So we're saying we're flying over the Earth's surface from east to west rotation, so over the equator kind of. And we want to figure out the distance we're traveling. We know the diameter, we want the circumference around the Earth. So to do this, we would do pi times 12,756. Actually, no, we would not. We would use the miles. So not the kilometers, because we want the answer in miles, so we can use this later on. So let's say times 7908. And this gives us, so I'll erase this for now, pi times 7908. 24,844. This is miles. I'll just put M. Actually, I'll write the full thing. Miles. Okay. So they get approximately the same. It's a little bit off, but it's about ballpark 24,000 miles. And then finally, note that we want the 150 miles per hour. I'll erase this here. So we have this value here. Let me highlight that. So we have this. We're going to use this, and we're going to multiply it or divide. So here we're going to divide. So we're going to take this. The equation that we're using is speed is distance over time. We want to find out the time. So time is distance over speed. So to manipulate this equation, we just switch t and v. We switch the positions. Just by using algebra, you can kind of see how that works. And then we have distance, so this value divided by velocity, which is this value right here. So we'll do that. So I'm not going to write out the numbers. I'm just going to do it in my calculator. 24,844 divided by 150. And we can see that since we have the units, we'll have miles for the distance and then miles per hour. So the miles cancel out, and then the hour goes to the numerator, and we're left with the units hour, 166 hours. And that's our final answer. So looking at time, they calculate, so they do the same thing here. They end up with 166 hours. So that's kind of the step-by-step process to answering this question. Once again, just to summarize, they've given us some extra values that we need to kind of figure out what we actually need based on what the question is asking. So it's good to write out these values, but then look at the question and figure out which values you really need. And we end up with 166 hours. So correct answer. Great job. Mark this as correct and move on to the next question. So question number 4. Alright, so question number 4, we're asked, what is the period of a wave? So looking at the junior tutor's answer, we can see that they've defined it based on this plot. So whenever we're thinking about a wave, we think about kind of some sinusoidal wave like this. We're talking about the period, we're thinking about how long does it take to complete one cycle of this repetition. So we can see they start off at this point right here. This is one cycle, and then it repeats again, and so on. And same the other way. So one period is just the time right here, since we have the x-axis is labeled time, y-axis is labeled position. So here the period is like a time unit. So here we take one cycle and based on the x-axis calculate that. So I'll draw a little diagram over here to give you some other examples to think about. So this is question number 4. So we'll draw some, we have time over here, and then position. Let's say position X. Let me erase that. So position X. Alright, so essentially, so this is one example. I'll give you another example. It doesn't matter what the wave looks like. You can still figure out what the period is, so I'll use a different color here. So let's say we had a wave like this. No, these aren't 100% identical. So if we had something like this. So what I was trying to do there is this and this is the same as this. So there's 3 repeating units of the same waveform. And here all you'd have to do is look at the x coordinate over here. So actually I'll use a different color. So you look at the x coordinate over here, the x coordinate over here, and just do some subtraction to get the period, and the period would be just this distance right here. So from here to this, and that will be your period. Usually period is defined as T, capital T. And then the other thing that's important to know is, so here they have the definition: the period of a wave is the amount of time taken by one cycle to complete in a wave. The wave period T of a wave is the inverse of frequency. So a very important formula to know is that period is the inverse of frequency. So units for period is in seconds usually, or some unit of time. Usually it's seconds. And then frequency, units of frequency is in hertz. So if we were to calculate, let's say, frequency would equal 1 over the period, and that would be in hertz. Or per second, right? So hertz is just 1 over seconds. So that's kind of a general overview of what is a period in a wave, how to get it from a graph, and kind of the units used to calculate it, and how it relates to frequency. So, great explanation. Answer correct. So we'll mark this answer as correct and move on to the next question. Alright, so question number 5. So here we're asked, what is the specific heat of air? Just give me a second. Alright, so specific heat of air, here the unit to answers is approximately 1 kilojoules per kilogram Kelvin. So you can see there's pretty complex units. It's essentially kilojoules per kilogram Kelvin. I'll explain to you why this is the case in a second. Here's the definition of what specific heat is. The specific heat of a material is defined as the quantity of heat required by a unit mass of the material to rise its temperature by 1 degree. To raise its temperature by 1 degree. The specific heat of air depends on temperature, so temperature changes when the specific heat of air also will be changed. But the value is approximately this much. Okay, so when this value, so often when we think about specific heat, is represented by the constant C. So for all materials, they have a specific heat. So specific heat of air is just 1. And it's often used in this formula. Q is equal to mc delta T. So this is C right here is specific heat. So I'll define all the variables. Q is the heat energy. M is mass of the material. C is specific heat. And finally, delta T is change. So delta, whenever you see a delta, it means change. And this is in temperature. Okay. So this is kind of the equation that you should know right here. And when we look at this equation, if we're given, let's say, a specific, question, this is more of a general topic, but let's say we're given the heat energy, we're given the mass, and we're given the specific heat of, let's say, some material, right? Here we can calculate the change in temperature that would occur based on the heat energy added, the mass of the object, etc. We know how much temperature, the change in temperature, what will happen. So if it was at 25 degrees, how much it will increase or decrease based on the value calculated. So this is where specific heat is useful, and usually specific heat is found for different materials in a table, and depending on the question, usually it's given or you have to look at a given table to find this value. So that's kind of a general overview of what specific heat is and we've kind of also given the value of the specific heat of air. So, great work. Correct answer. So I'll mark this question as correct and move on to question number 6. All right. Alright, so question number 6. Alright, angular velocity equation. So we're trying to find what is angular velocity. So the variable that is used for angular velocity, so I'll write that down, angular velocity. So the variable for this is kind of like a W, a curvy W. I forget the exact Greek name for this, but this is kind of the symbol that we'd use for angular velocity. So let's go through the Janine The Tutor's solution. Angular velocity refers to how fast an object rotates or revolves relative to another point, how fast the angular position orientation of an object changes with time. There are two types of angular velocity, orbital angular velocity and spin angular velocity. So here we're giving kind of a general explanation. So essentially how to calculate it is as follows. So angular velocity is the change in the angle over the change in, when we're saying theta, change in theta is this angle right here. So in this diagram, we're looking at this angle. So maybe it would start off in this line, and then it would move on to this line. So we know the change in the angle over some period of time will give us the angular velocity. And the units are in radians per second. So that's the units for angular velocity. Another way to think about it is using this equation over here. So we can also use speed over radius. So speed is what the object is moving at this point, the vector at that point in time, divided by the radius, so the distance here. We can also think of it in terms of frequency. Frequency is revolutions per second, so angular velocity can also be 2 pi f frequency. So this is often dependent on how the question is phrased, what the givens are, and so on, but usually when I think about angular velocity, this is the main equation I think about. It gives you kind of what it means, what it truly means. So change of the degrees or the angle over some period of time. That's angular velocity, and that's kind of similar to what linear velocity is, right? So velocity, just linear velocity. If we look at it. So we usually represent this by v, so I'll write it down here, is equal to, let me actually erase some space. I'll put it right here. So v equal to change in distance over change in time. So we can see right away how this relates, how these two kind of mirror each other. Here we're using a linear distance or a linear change in position. And then here we divide by time. Here we're using a change in angle, dividing by time to get angular velocity versus linear velocity. So this is kind of a general overview of what angular velocity is and the equation that you can use to solve. Another thing I want to note for this diagram, here we're given also theta is s over r. S is the arc length right here, this distance right here, divided by r. And that gives us the angle right there. So we'll mark this answer as correct. So great work, correct answer. And we'll move on to the next question. I think that's all I want to say for this question. Alright, so question number 7. Alright, so question number 7. What is specific gravity? And write its formula. So, specific gravity, let's look at the junior tutor's answer. So definition, it is defined as the ratio of the density of a given substance to the density of water at 4 degrees. So this is kind of just a word definition, and here's the equation. So specific gravity represented by S, and we have subscript G is equal to the density of some substance or material. So this value would be found in a table. So usually you'd be given this value in the question if you're given, a certain math problem to calculate, or if you want to calculate the specific gravity divided by the density of water at 4 degrees. So one thing to note is the specific gravity for water. Just looking at this, you can kind of think about, okay, if I wanted to find the specific gravity for water, I would take the density of the substance, in this case it would be density of water, divided by density of water, and we know that that would be just 1 for the specific gravity of water. But let's say we had some other substance, so a denser substance than water, then our specific gravity would be higher, because our numerator would increase, but our denominator would stay the same. That means this whole fraction would increase and we'd have a higher specific gravity. But let's say we had a lower density for the substance than water, and we'd have a lower specific gravity because the density of water stays the same. So this is kind of just the general formula for specific gravity, and it's essentially just a ratio. And here you'd kind of just plug in the value based on something you found in a table or something given in the question, and that would give you the specific gravity of that substance. So great work. Answer is correct. And we'll mark this question as correct. Alright, so question number 8. So question number 8 also relates to specific gravity. So in this question we're asked, what is specific gravity and its units? So let's read through what the junior tutor explained. So specific gravity, specific gravity is the ratio of density of a substance with respect to another reference substance. So this is also what we talked about in the previous question. Generally, this reference subject is assumed to be the water, and hence we can define specific gravity of a substance as the ratio of density of the substance with respect to density of water. So this is the equation. It is the same equation we used before, so specific gravity, I'll write it again, is the density of some substance over the density of water. Alright, so since it is the ratio of two densities, that's why it is... Oh, so wait. So here we're asked what is specific gravity and its units. So we want to know what units does specific gravity have. So looking at this ratio, we can see that there's units for density. So density is mass per volume. So just give me a second over here. So density, the units of density is kilograms per meters cubed. So this is kind of the SI units. It could be grams per meters cubed or grams per centimeters cubed, but it's mass divided by volume. So here, if we have the same units on top, same units on the bottom, the units cancel each other out. So we end up seeing that specific gravity doesn't even have units. It's a unitless physical quantity. And this is what the junior tutor indicates here. Since it is the ratio of two densities, that's why it is a unitless physical property. So let me just Google a specific a density of some object. So we know density of water is 1,000 approximately kilograms per meter cubed. Let's say density of, say, steel or something. So steel is more dense, so density of steel is equal to 8,050 kilograms per meters cubed. So here we can see we would take 8,050 divided by 1,000, and we end up with Sg is equal to 8.05. And there will be no units because the units cancel out. And this would be the specific gravity of steel. You could use other subjects, more dense, less dense, and so on. That's kind of an example of how to calculate it and what the units are. So write a comment here. So your job answer is correct. And we'll mark this question as correct. And that's all I want to say for this question. Alright. Alright, just give me a second before we start this question. Alright, so this question is question number 9. Alright, here we're asked Hooke's law equation. So we want to know what is Hooke's law equation. So here, Hooke's law, to understand Hooke's law, first we should understand elasticity. Elasticity is a property of material by virtue of which it restores its natural size. So this is the key here. So the material restores its natural size and shape or dimension on removing the deforming force. So a force which has a tendency to change size and shape of the body. So Hooke's law, often we relate it to a spring. So we have some spring attached to a mass. And this spring has a spring constant, so K. And there's some force acting on the spring, F, and there's a change in distance of the object, because the force will pull on the object over here, so force. And this is kind of the setup. And there's going to be some change in distance. Or, yeah. So here, this elastic force, which acts against the deforming force, brings the body back to the original shape. So we're talking about the elastic force, and then there's the deforming force. So Hooke's law gives a relationship between the force applied to an unstretched spring and the amount the spring is stretched. So Hooke's law, force needed to extend or compress a spring is directly proportional to the extension or compression of the string. So here we're given kind of a little diagram and some explanation here. So essentially what the equation that for Hooke's law is, force is negative K delta X. And we can kind of think about this. So if delta X pulls in that direction, so in the direction illustrated here, so let's draw that again in green. So if we have Hooke's law pulling in this direction, we know that the spring is going to be stretched. So there's going to be a force, a restoring force. So here we're defining this as force of the spring. So So I'll write that down here. S. So if we have a stretched spring, let me just erase this a little bit, make some space. We know that if a spring is stretched, so I'll draw something like this. We know that the force is going to be pulling in this direction. And that's why there's a negative sign right here. Because if we have a positive delta x in this direction, we're going to be pulling the spring in this direction. That means the spring is going to be stretched. The force that the spring has, the restoring force, is acting in the opposite direction. Similarly, if we were compressing the spring, so let's say we were compressing, it was like super compressed, we know that that means we're pushing the applied force, so we'll call this Fa, is pushing in this direction, Fa. That means the change in delta x is also in this direction, so this is negative direction. The left is negative, the right is positive. Therefore, if we have a negative delta x over here, it cancels out with this negative, and we end up with a positive spring force, or restoring force. And the spring for restoring force will be pushing back, right? So it will be acting to the right side for this spring. So the general formula that you really need to know is the one on the bottom of the screen, so I'll highlight this for you. So this is the equation for Hooke's law, and essentially it's the spring constant times change in delta x, so distance, and you'll get the spring force or restoring force. So just quickly outline Hooke's law. What Hooke's law is, it gives us the relationship between the force applied in an unstretched spring and the amount the spring is stretched. So if we had some constant and a delta x, we can calculate the spring force, and if we're given, let's say, spring force and the delta x, we can calculate the spring constant, and so on. So this will depend on what the question is giving you, which values are given, and you can just plug these in and manipulate the equation to get the answer. So, great job. Answer is correct. So I think that's all I'd like to say for this question. I'll mark this question as correct, and we'll move on to the next question. Alright, question number 10. Alright, so the topic we're covering here is buoyant force. So buoyant force equation on buoyancy. So we're talking about the buoyant force, what is the equation, and so on. So let's run through what the Janine The Tutor responded here. When an object is immersed into a liquid wholly or partly, so if we have some liquid, so let's say we have the liquid, something like this, so we'll see the liquid is down here. So this is the liquid. I'll actually erase this. We have some object either down here, fully immersed, or if it's like partly immersed, we'll have a buoyant force. So this is kind of, here I'll use a different color. So this is the liquid. We have an object. I just drew a box to represent this, either if it's completely submerged or partly. We have an upward force, so a force acting upward. Call this FB. Similarly here, FB. And that's the buoyant force. So according to Archimedes, this buoyant force is equal to the weight of the liquid displaced by the portion of the body inside the liquid. So this is key to know. The buoyant force is equal to the weight of the liquid displaced. So we're only thinking about the liquid displaced by the object, by the portion of the body. So if it was half the object, we're only looking at half the volume on the bottom, or if it was the full object, we're looking at the full volume of the object. Now the question comes to mind that what much liquid is displaced by the body? How much liquid is displaced? So how much liquid is displaced by the body is the volume of the body inside the liquid equals the volume of liquid displaced by the body. So essentially what this is saying is for any object submerged, the volume of that object will be the same as the volume displaced by the object onto the liquid. So from this, we can conclude buoyant force is equal to the weight of the liquid displaced. So this is the key things right here. So the volume of the body inside the liquid. So we have some object over here. We have a volume, whatever it could be 3 meters cubed. Is equal to the volume of the liquid displaced by the body. So whatever it displaces, that's the volume that we care about. So if this was half, we'd look at 1.5. If it was full, it would be 3. From this, we say buoyant force, so FB, this is equal to the weight. Weight is measured in newtons, so weight of the liquid displaced. So weight of liquid displaced. That's the key thing you want to know here. Okay, so finally we get to the formula. So the formula here is FB. So I'm going to write this in green. FB is the density times the volume times gravity. So this is really the formula. This is how I write it. Here they wrote it a little differently. So B is just capital B, buoyant force, similarly over here. Density is shown here. And it's the fluid density in kilograms per meters cubed. It's this symbol represented here. It's like a P. I forget the name of the Greek name. And V is the volume, displaced body volume of the liquid. So this is important to know. It's not the full volume. So if it's half submerged, it would not be the full volume of this object. It would be just half. If it was fully submerged, then it would be the full volume of the object. And G is just standard acceleration due to gravity. And the buoyant force always acts upward on the object. So when the object's going into the liquid, the buoyant force is the force acting upward. So let's say we were given the density, given the volume of the object, given the gravity, and we're asked to, we know gravity is 9.8 meters per second squared. Let's say we're asked to calculate the buoyant force for an object that's submerged 3/4 of the way, right? So what we do there is we take 3/4, multiply that by the volume of the entire object, and that gives us this variable V. We're probably given the density, and we know gravity. We multiply those through, and we end up with the buoyant force. One thing to note is buoyant force is measured in newtons, so that's important to note as well. Any force essentially is measured in newtons. Alright, so answer is correct. Let me just write a comment here. Great work. Alright, so I think that's all I want to say for this question. We'll mark this question as correct, and we'll move on to question number 11. Alright, so this question is asking us how to find average speed. So average speed, one second, let me just erase that. I'm going to number this as question number 11. Average speed is represented by V average and is equal to change in distance or change in time. One thing to note for average speed is we don't really care about the path that is done. We only really care, actually let me rephrase that. So it's the distance traveled. So we do care about the path, I believe here. Yes. Let me think about what's the situation where we don't. So if it's velocity, so if it's a vector, that's when we don't really care about the path. When it's average speed, we do care about the path. So that's kind of the differentiation that I was thinking about. So when it's average speed, we do care about the path. When it's a vector, so a velocity in an instant in time, or between 2 points, if it's a vector, we don't care about the path traveled. We just care about the position. So let's run through the Janine The Tutor's explanation. When the speed of a moving object is varying, the average speed of the object between any two intervals is obtained by dividing the distance traveled during the time interval by the time taken to travel. So delta d, so change in distance or change in time, which is also the same as saying d2 minus d1 or t2 minus t1. And this is just saying at position 1, at position 2. So you're at position 1 at this period, at this point, you're at position 2 at this point. So this is kind of a word equation. So average speed is distance traveled over total elapsed time. So let's say we've traveled 20. Actually, let me give you some points here. Let's say this point, point 1, is 2 and 10, and then point 2 is 4 and 2. Does that make sense? No, that does not make sense. So we'll say this is 30. 4 and 30. Okay. So this is point 1, point 2. So we can see because the x coordinate is time, so we're 2 at time equals 2 seconds and 4 seconds, and then the y axis is distance, so at distance 10, let's say meters and 30 meters. So plug these in. Let's draw a line here. We'd say 30, so d2, which is right here, minus d1, which is 10, divided by t2, which is 4, minus t1, which is 2. So we end up with 30 minus 10 is 20, 4 minus 2 is 2, and 20, we get 20 divided by 2, and then doing this we get 10 meters per second. And that will be the average velocity for this example. So this is kind of a rough example of how you'd find the average speed, but really the main equation that you want to use here is this right here. This is really the main equation that you care about for any question that you're given where you have to calculate the average speed of a system. So we'll leave a comment here. So excellent. Answer is correct. Alright, so this is the final question that we'll be answering for this session. So I'll mark this as correct. Okay, so thanks for tuning in to this OneClass session. Hopefully you found the questions that we went through to be helpful, and I helped you guide through the process of how to solve each physics problems. If you enjoyed this session and found it helpful, you can always go to oneclass.com for any tutoring help or homework help. You can also visit the website in the description and subscribe to this YouTube channel for more content like this. Hope to see you in the next session. Goodbye for now.